Friction is defined as a force that resists the attempt of motion due to contact between an object and the surface it's on. We've already discussed that the contact between the object and the surface it's on is the normal force. And so if we analyze a mass on a surface like a ground or the table, what we first have to recognize is that down here, if we were to blow this up using a microscope, the actual surfaces are not smooth. And so there are irregularities within the surface that cause the surface to have some bumps and ridges. And this is true both in the material of the mass, M, and also the material of the table or the ground. There are irregularities that cause the surface to have irregular shapes, bumps, and motion. So when I attempt to move mass M by pushing on it with a force forward, F, an applied force, that attempt at motion causes these teeth to push against each other. And so we end up with a counter force, which could be described as a normal force at each individual surface and summed together to create a resistive force to the motion. This is a comprising factor of friction. However, materials, when put in close proximity due to a contact, so if the weight is pushing down in such a way that these become very close together, what we also need to remember is that the materials are made of atoms, right? All materials are made of atoms, and all atoms have electrons on their exterior shells, their energy shells, their orbitals. So these electrons are common, right? All electrons are exactly the same from one side to the other. No matter what atom I'm looking at, all electrons are the same. So if I push these two materials close enough together, it's not unusual for one electron to dissociate from its parent atom and move across to another atom, and vice versa. So these electrons exchange back and forth between the materials. That exchanging of electrons has a name. It's called van der Waal forces. And it creates a small interaction that can be thought of sort of like adhesion, but not exactly. And this is simply because the electrons are common, they have no loyalty to their parent atom, and as they exchange across, it creates a very, very weak force called van der Waal forces. Van der Waal forces add to the resistant forces of these irregularities in order to generate a stationary friction that is larger than when the object actually breaks free and is in motion. Once it's in motion, these electrons gain relative momentum. We can imagine that the momentum of this would be 0 if it's not moving, and then the momentum of this one would be forward. And so all the electrons in the mass end up moving forward. So they have a tendency to stay with their atom because the atom is moving while the electrons are moving, while the mass is moving, whereas the electrons here are staying with their atoms that are stationary. So this van der Waal force only happens during the stationary state and is much less likely during the movement state, which means that friction actually carries two states or two types of friction. The first of which is the static friction component, and this is when the two objects are stationary. And so the action of pushing on it is being resisted by the interlocking of the irregularities of the surface and the van der Waal forces adding together to resist the motion. Whereas in kinetic, this is while the objects are moving relative to one another. Either the ground is moving this way, or the object is moving that way, or both. In that sense, the van der Waal forces are not a prominent factor in the analysis of friction and just the irregularities of the surface. And so the static is always greater than the kinetic in terms of friction. And so this leads us to the analysis of how we actually calculate friction. Remember that friction is based on contact between the surfaces. And so the way we measure contact between the surfaces is the normal force. So F of F is directly proportional to F of N. However, you can imagine that if this mass was made of some material and we put this on concrete, that would be a different friction value when I attempt to move it as if I took this mass, same material, and put it on ice, or put it on Teflon, or put it on something slippery. So the material matters in the interaction, the material from one side to the other. This is described as a proportionality constant using the Greek letter mu. So the friction force is dependent upon the stickiness between the surfaces, mu, and the contact between the surfaces, F of n. This is the formula for calculating friction. So F of n we've seen as a contact force, and we'll be able to calculate that through a force analysis of the various other forces acting within the system, and then mu is going to be a material-dependent characteristic. And what's interesting about that is, as we see above, the normal force is simply an action based on all the other forces in the system, right, which doesn't change. And so the material-dependent characteristic is actually going to have two versions. It's going to have the static version based on the ability of it to exchange van der Waals forces, and then it's going to have the kinetic version, which is going to be while it's moving. And so these values will be specific to the case of whether or not it is not moving or it is moving. And so what we can see is that as we have an object having an applied force causing it to attempt to move, then friction is resisting as a static case, balancing out whatever applied force, causing the object to remain at a stationary state of an acceleration of 0. But then once it breaks free and begins to move, friction doesn't go away. It's just reduced by that van der Waals value. And so the kinetic value is a lesser value than the static value. And so what's most useful is to look at it as a graph. So if I analyze the friction force based on the applied force, as I apply a force, the friction force increases in order to match that value, right? And so a low amount of applied force results in a low amount of friction force. This helps us recognize that the friction force can never exceed the applied force. If that were such a case, then when I go to push on this with a forward force F, a resistant force F of F acts backwards, right? It's equal and opposite in the opposite direction. But this friction force is an act of a reaction to this force. So this could never exceed the applied force Fa, because if that were true, then friction could cause an object to move backwards. And that's not what friction does. Friction resists the motion, but doesn't actively create the motion. And so in analyzing the values of F of F, we go. This section is the static analysis where the acceleration equals 0. But at some point, the friction value gets to a maximum value, right? And then the applied force exceeds that, right? And so then the applied force causes the object to accelerate and move forward. So what happens is it breaks free. So if some discontinuous function then drops down, and then from then on, we have the kinetic case. Here, the friction value remains a constant despite an increase in an applied force. And this has to do with the interaction between the surfaces and the normal force solely, right? So once this starts to move, the resistance is the grinding of the two irregular surfaces on average, causing a force to resist that motion. It doesn't go away. The friction doesn't drop to 0, but it does drop down. And so what we see is that it's actually easier to keep an object moving than it is to get it moving. And that should make sense, right? This, in combination with momentum, describes why you would want to keep an object moving once you get it moving, because once you come to a stop, it goes back to the static and matches you back up to this peak again. And we'll be looking at a few examples in the next video on how to analyze this together. What is important to say is to note that in the example that we just saw above, this mass, m, the applied force was forward, the friction force was backwards, because the friction force is always opposite to the applied force. But due to the gravitation, down, the normal force, the contact with the surface pushing up, was up. And what we see is that f of f equal to mu times f of n is a scalar relationship, right? There is no vector arrow on top of these because f of n is perpendicular to f of f. And we would generally say that these two things are independent. And they are in terms of directional vectors, they are independent. But in terms of the physics, f of n is causing these things to touch, which is really causing these two surfaces to come within contact that these ridges matter. So a relationship of combining the vertical direction to the horizontal direction back in our two-dimensional analysis of dynamics comes from the friction force, right? So this is a scalar formula that allows us to relate, in some cases, a vertical force to a horizontal force. And we will find that in general, the normal force and the friction force are mostly perpendicular to one another based on the interaction of the way the system works, right? Because generally, we are pushing perpendicular to the direction that the surfaces are in contact. And so this will become relevant as we look at various surfaces and various orientations as we analyze the system. But what we need to remember is that in the free body diagram, we cannot see the motion, right? But we can see the result of the motion based on the friction. So if the object is attempting to move forward, then the friction force is resisting that. We can infer the direction of motion based on the friction force.